We are ready.
All right, so we have Nils Carqueville, who will tell us about symmetry defects and equivariant completion.
Thank you. My talk is about two-dimensional topological field theories with defects, and it can be viewed as a sort of continuation of Daniel Plenzner's talk from earlier today, where I will now focus solely on the general theory. I will, however, not assume that you actually had the pleasure of attending Daniel's talk, so it can be enjoyed independently of his talk. I shall start by explaining and reviewing how ordinary orbifolds can be understood in terms of defects and also generalized, which leads to a notion that we call equivariant completion, which I want to explain and discuss some of its basic properties. And from that, one may wonder that since many topological field theories actually come from the twist of some richer theory, which is supersymmetric, whether if this is the case, what we can see from this orbifold construction about the supersymmetric aspects. This will lead us in this talk to some natural, interesting algebraic structures like Hochschild homology, cohomology. But there will be a question which I will hope to answer towards the end, or at least sketch an answer of, from the perspective of fully extended two-dimensional topological field theories. But before we get there, let's start with 2D TFTs with defects. These are functors from Bordisms to vector spaces whose purpose in life is to compute correlators. So more specifically, these Bordisms come with an orientation and with a choice of one-dimensional submanifolds inside of them that are labeled and oriented as well. And also the faces of the two-dimensional Bordisms are labeled by some set of labels, which I call theories. And also the one-dimensional submanifolds are labeled by another set that I call defect lines. Now, the details I don't want to discuss because part of the purpose of the talk is to try and convey a certain algebraic picture, which is natural to describe such TFTs. But before we get to any of the details, I would like to show you one rough idea, one rough picture how these generalized orbifolds come about. So if we have two theories, little a and little b, then we say little b is a generalized orbifold of little a if every correlator in B theory can be computed as a correlator in A theory, possibly in the presence of some network of defects of a special kind that is called A. Part of the reason for the name is that ordinary orbifolds are of this kind, where now A is some theory that comes with an action of a symmetry group G, and there's a natural way to encode the symmetry group as a defect, as a topological defect. And then the theory B is simply the ordinary G orbifold of that theory, if you can perform the orbifold. Another class of generalized orbifolds is where we are in the situation, again, where we have two possibly very different theories, A and B, and the defect X between them, which has the sole additional property that its quantum dimension is invertible, meaning that if we compute a correlator in B theory, where by the dashed lines they indicate that this is not the whole Bordism or world sheet, but just a small part of it, there might be a lot more going on outside. The value of this correlator is the same up to this constant, which is the dimension, namely this loop. So we create islands of theory A in this ocean of theory B. And since we are in the topological sector, we can expand these islands, which happens in the next step. Now, nearly everything is this pale theory A here. And you can convince yourself that the defects X come very close to each other, always in such a way that one is oriented upwards and one is oriented downwards. So the opposite orientation I call the dual of a defect. And if we say that the fusion of the dual defect with itself is called A, then if we fuse everything together in the end, we are in theory A, together with a network of green defects that are called capital A. Okay, so this is the basic picture. And in order to describe how to do this rigorously, it is natural to talk about bicategories. So recall that a bicategory comes with the following data. It has objects that are called little a, little b, little c, and so on. Then for every pair of object, a, b, there's a category whose objects are called one-morphisms, and they are denoted by capital X, capital Y, and so on, and whose morphisms are called two-morphisms of the bicategory script b, which I denote by small Greek letters. There's, of course, the ordinary composition of two morphisms, that is, morphisms in these bunch of categories, but you can also compose one morphisms because there's a functor called tensor product or tensor product, which is always defined if you have a category from A to B and then another one from B to C, and then this maps into the category associated to the pair AC, the ordered pair AC. Finally, for this product, there's also a unit that is special one-morphisms for every little object little a in the bicategory, together with natural isomorphisms, which describe the action from the left and from the right of the unit one-morphisms on any object, and that's associativity. And these isomorphisms must be natural and obey certain coherence axioms, which make everything well-defined and nicely computable. But the details don't matter for us. What matters to me personally is that usually when I think of bicategories, I have these little red words in my head. So objects are theories, something that you associate to two-dimensional faces of the Bourdism or worldsheet. One-morphisms are one-dimensional defects between these faces. And two-morphisms are associated to zero-dimensional things, so points where you can insert fields. Furthermore, these tensor products are the fusion of the defect lines, and the units are simply the invisible defects, which do not impose any extra condition on the bulk fields on either side. In pictures, it looks like this. Objects are labeled two-dimensional faces. One-morphisms are defects between these theories, and between the defects, we have two morphisms, that is, fields. Fields are composed vertically, so that's the operator product, and defects are fused horizontally. So the tensor product, which is the additional product here, is written in a horizontal fashion. So these are the kind of pictures I always have in mind when I think about bicategories. But just a plain bicategory is not enough in order to describe topological field theory. You need more. In particular, since we have oriented defects, it's to be expected that there are adjoints. So we say a bicategory has adjoints. If for every one morphism from A to B, there's another one morphism in the opposite direction from B to A, called X dual or X dagger, together with maps from X tensor its dual to the identity, and then the other way, identity to the dual tensor X, which generalize the ordinary evaluation and co-evaluation maps for finite dimensional vector spaces in such a way that these identities here are satisfied, which you read from bottom to top and from right to left. So here's the co-evaluation, there's the evaluation, and the fact that, for example, this left-hand side must be the identity, which means this unadorned vertical line, captures for us that X dagger actually is the dual for X. For example, in the bicategory of categories and functus natural transformations, this tells you that X dagger is the adjoint to X. Okay, so this is then naturally to expect that we have this structure. And if you define, as we did on the first slide, a topological field theory with defects as a certain symmetric monoidal functor, then Davidov, Kong, and Runkel explained a few years ago how you can always extract a bicategory with adjoints from that. And if the functor, which is the TFT, is denoted like this, computes correlator, then I denote it like this, the associated bicategory. And the general idea is that if you endow this bicategory with an sufficient amount of extra data and structure, then you can get everything about the 2D TFT out of it. And we'll understand parts of this during this talk. Now here's a few examples of bicategories, roughly ordered by my decreasing lack of understanding. In particular, we have here three kinds of theories that come from supersymmetry, sigma models and B-twisted Landau-Ginzburg models. But there's also WZW models, so purely bosonic theories, which are associated with a certain bicategory of bundle gerbs. And they also have this structure that I'm talking about. So all these categories, apart from maybe the A models, at least I don't understand how you have adjunctions there in general. But all the other ones do.
What TT do you associate with the model?
There's a bicategory of bundle gerbs where the objects are bundle gerbs and the one and two morphisms are bimodules and module maps of these gerbs. This work by, among others, Fuchs, Runke, Schweiger, Zuschek, and Waldorf. In particular, there's a paper by Waldorf from 2007 that explains this structure. But this is only the bicategory. So if you want to know what the full functor is, then this is a different question. So here's just the bicategory, and we can ask what other structure do you need on top of that in order to have a full TFT? Okay, so remember earlier we had, it's too far away. We had this picture where theory B was described in terms of theory A together with a defect network. And now I want to explain how to understand this properly in the context of bicategories. So let's start with some nice bicategory with adjoints, which maybe later I need to be C-linear, so that's the spaces of two morphisms are C vector spaces, maybe even finite dimensional. That's certainly enough. Now I define what a new bicategory is, which I call the orbifold completion. First I tell you what the objects are. Objects are pairs made up of old objects, little a in script B, and one morphisms that go from A to A, which have a particular property or structure of being symmetric, separable, and Frobenius. So let's have a look at what this means. First of all, it's an algebra. So this one morphism comes together with a two morphism, which is the multiplication. It's a map from A tensor A to A, and another map. So we always read these pictures from bottom to top. Another map from the unit to A, which satisfy these properties here, which simply categorify in the weakest possible version what it means to be an associative algebra with unit. So that means that it's an algebra. If you rotate all these diagrams by 180 degrees, then this defines for you a coalgebra. So let's assume we have an algebra and a coalgebra. Then here's some more properties that this algebra and coalgebra can have. This property is called being Frobenius, this is called being separable, and this is called being symmetric. The details don't matter for the purposes of this talk, and then on the next slide, I promise to give you an idea why these many green properties actually play a role and are very natural. But for the moment, just bear with me. And let me tell you that one particular example, which is separable Frobenius, always is the one morphism which encodes the action of a symmetry group. More on that later. Now we know what the objects are in the orbifold completion. What are one morphisms? One morphisms are bimodules. That's to be expected. A bimodule is over something on the left-hand side is a map from A to B, is a one morphism from A to B together with an action of the algebra on the left-hand side, which is B in this case, on X, such that the usual left module properties hold. So you can either act with the algebra and then act again, or first multiply and then act, and acting with the unit is doing nothing. So a bimodule means that it's a left module and a right module. You can guess what the right module structure should be. Plus, we need that left and right action are compatible, so they just commute. Nearly finally, we need to know how to compose one morphisms. So the composition in this bigger bicategory is by tensor product over the intermediate algebra, which is defined by some universal property in terms of coequalizers. And the unit in the bicategory for this object A, A is the one morphism A, the algebra. A is the defect. A is the symmetry defect. And finally, two morphisms are in B orb, the orbifold completion, are two morphisms in the original bicategory, which on top of that are also bimodule maps. So they commute, they are compatible with the left and right action of the algebras. So here's a theorem that says that this makes sense in the following sense. If you start from a TFT with defects, and if you do an orbifold construction within that functorial setting of the TFT, and then construct here on the right-hand side the associated bicategory, that's the same as starting with the unorbifolded bicategory and then apply the orbifold completion from the previous slide. And checking that this is true boils down basically to checking that the property of this, the structure of the one morphism A, of being symmetric, separable, and Frobenius, is in one-to-one correspondence to these Pachner moves, because you remember at the beginning of my talk, we started with inserting 4 little loops of one particular defect, and then in the end there was a trivalent network on the Bordism, which amounts to a triangulation of a surface, and any triangulation of a surface can be moved into another triangulation of the same surface using such Pachner moves. So if and only if that's possible, then they are equivalent triangulations. So this is the algebraic description of having independence of triangulations of the defect networks. But what if we relax this condition? So if we say maybe we don't want symmetry for one reason or another, well, this theorem tells you then you won't have a TFT anymore, but maybe we find something else that is interesting, and I think we will. Now to discuss the property of being symmetric, you remember symmetry means this identity here. One finds that a Frobenius algebra is symmetric if and only if this particular automorphism here from A to A is the identity. Let me write it down because we'll need it later. For the algebra A, it looks like this, where we use all the structure that we have for A. So it's a map from A to A, where we use the multiplication, the co-unit, the unit, the co-multiplication, the co-evaluation, and the evaluation